Section 1.62, limits of sequences. A sequence is a list of numbers, an infinite list that sometimes might converge to a certain point. If it does, we say the sequence is convergent and its limit exists and is equal to some value a. A sequence can also be considered as a function whose domain is the natural numbers and whose range is, well, just about anything you want to assign to it. But most of the time, we just think of sequence as Sn, where Sn is approaching something, if it is convergent. The limit, the definition goes like this. Given epsilon, there exists a large enough number n such that the entire tail end of the sequence Sn is within epsilon of a, as long as n is bigger than the large n. So for all n that's bigger than a fixed point. So once you cut off the tail, the entire tail end, which is infinite number of stuff in there, has to all pack in within epsilon of a. So it's all in that little neighborhood. So when that happens, then we say the sequence is converging to a. Now let's look at an example of how this epsilon proof can be done. Say here's a fairly simple looking example. Limit of n goes to infinity. 2/3 to the power n is equal to 0. Now we need to show that. To show that, then by the definition, we must show that is 2/3 to the power n is less than epsilon. Or we can flip it around to say 3/2 to the power n is bigger than 1/epsilon. All right, how would you go about doing that? A lot of times in sequences, you have to cook up another sequence that's much easier than this one, because this one is not that obvious why it would go to 0. So let's come up with something that's easier to see that will definitely go to 0 and control it that way. Compare the two sequences. So what we're going to do first, let's write out the sequence. Okay, so our sequence looks, after it flipped around, looks something like this. It started at 3/2, and then 3 squared over 2 squared, and then 3 cubed over 2 cubed, and so on. And the increase here, how much does it increase? It increases by the increase in the sequence. As you can see, this sequence is increasing, and increased by at least 1/2 times 3/2, because the first item is 3/2, and each time it multiplies itself by 3/2, so it increases at least by that much. Well, more later, because each time it increases 50% of what's in the previous thing by multiplying itself by 3/2. It's like increase, but the least it will increase is by 1/2 times 3/2, that is 3/4. So that's a good increase. Now compare it to the sequence that's n/2. Okay, what does n/2 look like? n/2 start out being 1/2, and then 2/2, and then 3/2, and so on. So this particular sequence increased by a set amount. It just increased by 1/2. So the increase here is exactly 1/2. Now, as you can see from here, since this sequence started out with being 3/2, and it increased by at least 3/4 each time, whereas this one started out being only 1/2 and increases only by a 1/2 fixed every time. So it is clear then that the sequence, this particular sequence, is going to be bigger than this sequence right here. And that's for all n. Each term is going to be bigger. Okay, each time you put in an n, this value is bigger than that value, which of course means that if you flip it back around like this, if you flip it around again, the inequality sign is reversed. So this sequence is dominated by this one. And as you can see, this sequence is going to 0. And we're trying to show this sequence go to 0, and we found a sequence that is bigger and still go to 0. And that means we're in a good position. So the proof then is say that we will choose, given epsilon, we choose big N, choose n such that the 2 over big N is less than epsilon. Okay, in that case, then this particular value Then for all n that's bigger than the big N, we have 2/3 to the power n is going to be less than 2 over n, which is less than 2 to the power 2 over big N, because n is supposed to be bigger than big N, so this is smaller, and this which is less than epsilon. And that concludes our proof. Now to find something like this sometimes take quite a bit of work. That's why sequences are often considered challenging problems, but that's also what makes them more exciting. So each time we will pose some kind of a trick somewhere to solve a sequence problem, and we will look at the next video for the next problem.